Hi everyone, I'm recording this for you today because unfortunately I cannot come into school. I'm battling the stomach flu, but I do not want us to fall behind. So what we're going to do is we're going to take notes using the notes guide that the sub should be passing out to you. And I will also be posting this on Google Classroom as well as the PDF of these notes. It's not my most technologically savvy one, just because I'm not feeling too well. But hopefully it should get the job done, and we'll wrap up any questions you have on Tuesday. So our agenda, we're going to start with lesson 4.1, day 1. And our first slide is going to talk to us about angles and a very important word called the standard position of an angle. So for an angle to be in standard position, there are two portions of the definition. The first thing that you have to remember is that for an angle to be in standard position, the vertex has to be at the origin. So we're going to be putting angles on XY coordinate planes. And what you'll notice here in both of my examples is that the vertex, this black dot, is at the coordinate 0, 0. And pretty much 100% of the time, if we're on a Cartesian coordinate plane, we're going to be having that vertex at the origin. That's one of the necessities to be in standard position. The other necessity is that the initial side has to lie on the positive x-axis. So you'll notice here this blue ray in both this first example and the second example. That's my initial side, and I know the E's cut off. My Mac is kind of acting up right now. But this blue side is my initial side, so I don't care what kind of angle measure we're talking about. Your initial side will always be on the positive x-axis. What will differ is what we see from example 1 here to example 2 over here. And example 1, this is a positive angle. Now the big difference between example 1 and example 2 is that positive angles go counterclockwise. So notice my initial side here. Notice we have this little arrow that's coming up and to the left in a counterclockwise direction, so the opposite direction that a clock hands swing. This is a positive angle. On the other hand, negative angles are the opposite. They also start from that blue initial side, but instead of going up and counterclockwise, negative angles go down and clockwise. So this example on the left is a positive angle. This example on the right is a negative angle. So we're going to talk a little bit about circles and going back to geometry. So we have this image over here on the right hand side that you might have seen in honors geometry. We've got a basic circle who has a radius of r and an angle that we're going to refer to as theta. It's just a Greek letter. Corresponding with that central angle theta is an arc of length s. So let's go back to the basics. If we were just talking about this entire circle, how would we find the circumference of the entire circle? Well, circumference is 2 pi r. But what if we only wanted this red portion? Well, that red portion from geometry, we should know, directly corresponds to the central angle it's aligned with, so theta. So notice that theta is part of this entire circle. Well, you'll remember that a circle has a circumference of 2 pi r. Let's pretend that our r is 1, in which case we're talking about the portion which is theta here, out of the entire circle, which we're going to call 2 pi. So theta out of 2 pi is the portion of the circle we're referring to in red. So to find the actual length of this s, what we do is we take that central angle theta, divide it by 2 pi, and then we multiply by the circumference, which is 2 pi r. Doing some simple arithmetic here, you'll see that the 2 pi's will cancel, and you're left with theta r, which leaves me with one of my first formulas that we're going to be memorizing here. Theta is s over r. So I can find the central angle theta by comparing the arc length to the radius. So as we were talking about, the circumference of a circle is 2 pi r. It follows that the central angle is 1 full revolution. That corresponds to an arc length of s equals 2 pi r. So keep in mind that 2 pi, where you know pi is 3.14 approximately, so 2 pi is approximately 6.18, which means what we're doing is we're defining a radian as such. You'll see here that I have a little bit over 6 radians. And so I'm going to show you this video that actually does a really good demonstration of it since I'm not there to show it to you hands-on. Here's the video. Hopefully it's popping up for us.
This video illustrates the definition of a radian. First, begin with a unit circle. Now, consider an arc length equivalent to 1 radius. The measure of the angle subtending an arc length of 1 radius is 1 radian. If we double the arc length, so that now we are viewing an arc length of 2 radii, then the new angle is 2 radians. Note the connection between arc length and subtended angle. The formula for arc length is L equal radius times angle in radians. Put another way, the angle in radians is the subtended arc length L divided by the radius. In this way, the circle need not be a unit circle. For example, if an angle subtends an arc length of 12 on a circle with radius 6, then that angle has measured 2 radians, since 12 divided by 6 is 2. As this video is wrapping up, the viewer should note that a full revolution is not perfectly divided into an integer multiple of radians. The closest we can come is 6 radians. Yet this comes short of a full revolution. Perhaps it is helpful to recall that 1 revolution is equal to 2 pi radians, which is about 6.283 radians, slightly above the integer 6 radians.
Alright, so that video was just a general demonstration of what a radian is. We're pretty familiar with degrees, but for the most of this chapter we're going to be referring to radians. So it's a different way of defining an angle measurement that corresponds with the radius length. A lot of this doesn't make a whole ton of sense to you yet. We're going to start doing some examples here which should help you out. So here we go. We're going to be sketching angles in standard position. Determine in which quadrant the angle lies. Alright, so here we go. I do have it all worked out, and once again I apologize I can't be there to show this to you in person, but we're doing the best we can to make sure we're staying on track here. So the first example is negative 7 pi over 4. So there are a couple of things, and I'm going to go real slow, and some of you might get a little annoyed by it, but we got to make sure we wrap our heads around this. The first thing I want you to take major note of is the fact that this is a negative angle. Because it's a negative angle, that means this angle travels in a clockwise direction. That's very important to note. Another important thing to note is that we're supposed to be in standard position. One of the first things we defined today was standard position. Remember, for an angle to be in standard position, the vertex has to be at the origin. So you'll notice on my xy coordinate plane down here, I've got this little periwinkle dot at the origin. The second part of having an angle in standard position is that the initial side has to be on the positive x-axis. So I'm drawing it in right here. This is always my initial side. I don't care what the measurement of the angle is. The initial side is always on the positive x-axis. Now this is when we're going to get into fractions, and those of you who struggle with fractions, we're going to have to work through it pretty quickly here. Negative 7/4. If I change that into a mixed number, remember, 4 divides into 7 one time with a remainder of 3, which means it's 1 3/4. So 7/4 is the same thing as 1 3/4. Something you have to understand is this is 1 3/4 pi, where pi is a semicircle. So when we're drawing 1 3/4 pi radians, we're doing 1 pi, which is actually 1 semicircle. And then 3/4 of pi, which is 3/4 of a semicircle. So notice what we're going to do here. I'm going to start this, I'm going to do the best with the technology I have available right now. I'm starting on my positive x-axis, and I'm going to be going clockwise, 1 whole semicircle. So here I go, 1 whole semicircle like this, and now I've completed my 1 pi. The next thing I need to draw is 3/4 of a semicircle. So you'll see where I left off with this yellow. I need to do 3/4 of a semicircle. which I'm going to draw in right now like this. 3/4 is more than half. It's about that much. You'll notice in the green that I've drawn in quarters of a semicircle. So imagine having a semicircle cut into 4 pieces, where I've got this piece right here, a piece right here, a piece right here, and a piece right here. I need to travel through 3 out of 4 of those pieces. Also, please notice you must put an arrow where you're ending, as well as the terminal side. So what important characteristics do we have here? The periwinkle dot, the vertex, should be at the origin. The blue ray, the initial side, should be on the positive x-axis. You should be starting with a swirl motion from that blue initial side in a clockwise direction. 1 pi, or 1 semicircle, and then 3/4 of pi, 3/4 of a semicircle. Draw your arrow and then draw your terminal side, which is that final ray that I've drawn there. So remember, if this isn't making sense to you, you can always go back on your own time and replay this in a slower frame for you to follow. It will be posted on Google Classroom. But we're going to do lots of examples. So let's take a look at example 2. In example 2, we have 5 pi over 2. So I always like to think about that in its mixed number form. So 2 goes into 5 2 times with a remainder of 1. So 5/2 is the same thing as 2 1/2. Remember, that's a positive angle, and it's important to note that positive angles go counterclockwise. Counterclockwise. If I break this up into the 2 1/2 pi, the 2 pi is technically 2 semicircles because pi is a semicircle. So 2 pi is 2 semicircles, or in other words, an entire circle. And then we have 1/2 of a pi, or 1/2 of a semicircle. So when I go to draw this, remember, standard position says vertex at the origin. Initial side is always on the positive x-axis. And now we're going to be going counterclockwise, an entire circle. So if we go an entire circle counterclockwise, that means we're going in an upward direction and we're making a circle. Now notice when I make this circle though, I'm not connecting it. I'm actually going to leave some space here to make kind of a swirly, like when you doodle. The second part I have to take care of is that 1/2 pi. Remember, that's 1/2 of a semicircle. So that's going to put me at right up here. Yes. And then we're going to put our terminal side facing upward. Alright, I know that's really sloppy. I don't have a stylus with me. I'm using my mouse pad here. So we're going 1 whole circle counterclockwise, and then 1/2 of a semicircle, drawing our terminal side. Let's try another one. 3.75. I gotta say, this is probably the toughest one because you'll notice there's no pi attached to it. So we have to put things in relation here. Pi is approximately 3.14. So 3.75 is 0.61 radians more than pi. And remember, pi is a semicircle. Now this is a positive angle, so once again, we're going to be going in a counterclockwise direction. I've got my vertex at the origin, my initial side on the positive x-axis, and then I'm going to go 3.14, which is pi, or in other words, which is a semicircle. I'm going to go that counterclockwise because this is a positive angle. Then I'm going to go 0.61 further. So what's 0.61? Well, we know 3.14 is an entire semicircle. 1/2 of that would be 1.57. So that would put me down here, halfway in the middle, 1.57. And 1/2 of 1.57, or about 1.6, is about 0.8. So 0.61 is less than 1/4 of a semicircle. So we just go a little bit further, put in your arrow, and then draw in your terminal ray, your terminal side. I know that's really pretty. All right, 2 pi over 3. Now that one's already in a nice form for us. It's positive, which means we're going to go counterclockwise. We don't need to make a mixed number, so we're just going 2/3 of a semicircle. So we've got our vertex at the origin, our initial side on the positive x-axis, and we're going to go 2/3 of a semicircle we're going to go 2/3 of a semicircle. That's incorrect. That should be clockwise. My apologies. So when we go 2/3, that puts me right about here. Now you notice I've drawn in this light green here. If I had taken a semicircle and cut it into 3 equal slices. My goal is that you don't have to do that. But some of you really struggle with fractions, so you might have to in the beginning. Let's go to ones you might feel a little more comfortable with, like 435 degrees. That's in degrees, totally different now, so you should be a little bit more familiar. We're going to be comparing to known values like 180 degrees and 360 degrees. So 435 is pretty big. It's bigger than 360, so if I compare 435 to 360, it's 75 more than that. So our entire angle, our 435, is comprised of 360 degrees, or an entire circle, and then 75 degrees, so less than 90. Notice I've got my vertex at the origin, my initial side on the positive x-axis, and we're going to be going counterclockwise because this is a positive angle. First of all, an entire circle, 360 degrees. Remember, you're not actually connecting it to make a circle, you're doing this little swirly motion. Then after that, I have to go 75 degrees further, so less than 90, but more than 45. Draw in your arrow and your terminal side, and there's your angle. All right, negative 220. It's negative, so we're going to be going clockwise. Now 220 isn't quite as big as 360, and you'll notice when I do my calculations here, I'm not worried about the fact that it's a negative. I kind of dismiss that after I figure out that the negative tells me that this is going clockwise. So unlike example 5, I'm going to compare example 6 to 180 because 220 isn't quite as large of a number. So 220 is equal to 180 plus 40. So we're talking about a semicircle and 40 degrees further. So we've got our vertex at the origin, initial side on the positive x-axis, and we're going clockwise 180 degrees, and then 40 degrees further, so a little less than 45, which would be halfway into that quadrant. And I'm realizing at this moment we haven't been talking about what quadrant these angles lie in. So I'm going to quickly just remind you how the quadrants are set up. In the top right is quadrant 1, top left is quadrant 2, bottom left is quadrant 3, and bottom right is quadrant 4. So I'm not going to go back and redo all of these, but you'll notice that this example here, example 6, the terminal side is in quadrant 2. So we would say that's in quadrant 2. Alright, so let's move on to a new topic, coterminal angles. So coterminal angles are when two angles share the exact same initial side and terminal side. Or in other words, their arrows both match up. So you'll notice here that I have two angles drawn in, 3/4 pi and a big one, 19 pi over 4. They both have an initial side on the positive x-axis, and they both have a terminal side over here in quadrant 2. You'll notice that as long as we swirly, and we keep swirling an entire circle different, you'll end up at that same terminal side. So if we keep adding 360, you get back to where you started. Think about it yourself. If you do a 360, you're facing the exact same direction as you began with. So coterminal angles are essentially angles that look identical if you didn't have all the swirlies to back up how big they are. So some key facts are that there's infinitely many coterminal angles. So for example, if I said 8 pi over 5, find coterminal angles, if you continuously added or subtracted circles from that measurement, you would be finding an infinite number of coterminal angles. So essentially, angles that differ in either multiples of 360, which is a whole circle, or in multiples of 2 pi, another whole circle, I should say an integer multiple of 2 pi, those will be coterminal angles. Don't overthink it too much. So we want to determine two coterminal angles, and all they're telling me is they want one positive and one negative. So in my examples below, I'm giving one answer for each of those, but remember there's technically an infinite number of correct answers here. So this is all we do. You start with your initial angle. Notice in example 7, our angle is in radians. I know it's in radians because it has a pi attached to it. One thing I'm going to stress to you is if something starts in radians, keep it in radians. If something starts in degrees, keep it in degrees. Don't essentially baby yourself into putting everything into degrees because that's not going to help you long run. So if I want to find a coterminal angle with 15 pi over 4, all I'm going to do is either add or subtract 2 pi. Now I chose to start subtracting 2 pi. You could have just as easily added 2 pi. And remember, the key reason that we add or subtract 2 pi is we're adding or subtracting a whole circle. And coterminal angles are angles that are essentially a multiple of a circle apart. So I take the initial measurement, 15 pi over 4, and I decided to subtract 2 pi. Now to do that, of course, we need a common denominator. So I would get a common denominator of 4. 2 pi would become 8 pi over 4. Now doing some fraction subtraction, 15 pi over 4 minus 8 pi over 4 is 7 pi over 4. Notice that that is a positive angle. It's 1 3/4 pi if we want to think about it. Remember, our directions are find one positive. So I found my positive. Now I want to find a negative angle. Just keep subtracting 2 pi until you hit a negative angle. So now I take my 7 pi over 4 and I subtract another 2 pi, but I kind of already got to it, and I'm subtracting that 8 pi over 4, which is equivalent to 2 pi. So 7 pi over 4 minus 8 pi over 4 makes a negative 1 pi over 4, so I have both my positive and my negative coterminal angles. Example 8 is in degrees. I think you'll like this better. Remember, we have to find a positive and a negative. All we're going to be doing is either adding or subtracting 360 to get to those values. So I decided in this case to add 360 to start. So if I add 360 to it, 38 degrees is a positive coterminal angle. Now I also wanted a negative coterminal angle. So I could take that negative 322 and subtract 360 to get negative 682. Remember, if you're bored, you can keep subtracting 360, or adding it, and you'll get an infinite number of correct answers. But our directions only tell us that we have to find one positive and one negative. So now going back to geometry quickly, complementary and supplementary angles. You want to remember that complementary angles have a sum of 90 degrees, or in radians, what's called pi over 2. Supplementary angles have a sum of 180 degrees, or what we know as pi radians. Notice this direction says, if possible, find the complement and the supplement. So we're going to start easy with example 9, a degree problem, 49 degrees. If we want to find something complementary to that, we have to find out what do we need to add to 49 to make 90. So all we do is 90 minus 49, and 41 degrees is the complementary angle. Supplementary, we do the similar process, except for supplementary angles add to 180. So what do we need to add to 49 to make 180? Well, 180 minus 49 makes 131. That's your supplementary angle. Alright, now let's look at example 10, which is 8 pi over 5. Before you start rushing here, I do want you to think about what would you do here with 8 pi over 5. Well, 8 pi over 5 is unfortunately in radians. That's 1 3/5 pi. I want you to look at the fact that it's 1 3/5 pi and think, what does 1 3/5 pi look like? Well, that's 1 pi and 3/5 of pi. So that's an entire semicircle and then some more. If something is larger than a semicircle, an angle measurement larger than a semicircle, so larger than 180, can it have a complementary angle? No. So my question to you now is, can this one also have a supplementary? If it's 1 3/5 pi, it's larger than a semicircle. The answer is no. So there's also no supplementary angle. So there's no supplement. I'm not going to write the whole thing out, but you get the idea. What would I do if it was an angle that was measurable? All I would do is the same thing I did over here in example 9, but instead of doing 90 minus the angle, I would instead replace that with pi over 2 minus the angle. To find the supplement, I would do the similar thing, do pi minus the angle. My warning to you with radians is you're not very comfortable with them yet, so when you're finding that supplement and that complement, make sure that you're checking first of all if it's possible. Alright, finally we're going to wrap up with converting between degrees and radians. So we have these two important facts, that pi radians is 180 degrees. So you're going to do a little bit of dimensional analysis here to change things from one mode to the other. So for example, in example 11, we're starting with 23 pi over 12. We want to rewrite that in degree measurement. So I'm going to blow this up. Alright, so 23 pi over 12, what are we going to do? Well, if you think back to physics class or chemistry, stoichiometry, what we want to do is we want to take 23 pi over 12 and change it from radians to degrees. So essentially we want to cut this pi out. To cut the pi out, we need to have a pi on the bottom. That way they cancel, they cross cancel. So in this case, I'm going to use this ratio here, 180 degrees over pi. You can see I did the math down here. The pi's will cancel, and then I want to start thinking, what goes into what? Well, because I'm good at my times tables, I know 12 goes into 12 one time, and 12 goes into 180 15 times. Then I would multiply across. 23 times 15 is 345 degrees. Alright, now for the next one, we're going to change from degrees to radians. Negative 225 degrees into radians. So in this case, I'm trying to get rid of the degree. So in this example, I'm going to use this conversion in blue, pi over 180. The reason, once again, is I want these degrees to cancel. So I'm going to take negative 225 degrees and multiply it by pi over 180. You'll notice I put it over 1. That's just for me to acknowledge the fact that that could be written as that fraction. So similar to before, I can cancel those cancel those degrees. Then I ask myself, what goes into 225 and 180? I know the largest number that goes into that is 45. 45 goes into 180 4 times. 45 goes into 225 5 times. Now if I multiply across, I have negative 5 pi all over 4. So here's your homework. If you have time, you can get started in class now. Once again, I really do apologize I couldn't be there today, but I don't think you want me there getting you all sick. My goal is to be back on Tuesday. And please understand, I know that this lesson might be a little bit complicated for some of you, but use your resources wisely, talk to each other, use the internet and your textbook, which is also an excellent resource. Thank you. See you soon.